This is the answer that Nick gave. I've forgotten your name. Deborah gave, right? You should basically focus on people of color if the probability that a person of color has a gun is bigger than the probability that a white person has a gun. Okay? Fine. So this is, so if you are from the University of Chicago and you're one of these like famous Nobel Prize winning super rational people, you write down a model like this and you come to a conclusion like this and then you go, see, discrimination is rational. And you're done. The problem is we're not done because we want to actually test the model and see whether or not it's true. You've seen the stop and frisk numbers. In fact, the proportion the RPOC is high. It's, right? In fact, the New York City police are pulling over people of color much more frequently than white people, pulling over or stopping on the street. Okay, I think we can skip this question because you got the answer, right? It's good policy when it's B. It's good policy when the probability of a black person or a Latino person having a gun is greater than the probability of a white person having a gun. Fine. Here's what they actually find in the stops. Okay, in the stops, what they find is that the proportion of people of color who have a gun is 0.018, and the proportion of white people with a gun is 0.038. So it would seem that, at least in the context of our simple model, they're getting it wrong, right? It looks like the cops are getting the conditional probabilities wrong. That is to say, it would appear as if Bayes' rule is not holding sway here. Okay. Now, if the decision about who to pull over, what racial categories to pull over is made by the chief of police, then it's the chief of police that's doing Bayes' rule wrong. If that's a decision that is largely left to the judgment of the police officer, then it's the police officer that's doing it wrong. Since the chief of police started out as a police officer, the distinction may not matter very much. Okay, now, some math for you to do. These numbers are not so far from the truth. Actually, I made up some of them. Maybe I made them all up, I don't remember. Suppose that 5% of people in New York City carry an illegal gun. What's that? What do we refer to that number as? Sorry? It's the probability of carrying a gun, which is a base rate. Right? That's the base rate. The hypothesis we're trying to infer is, are you carrying a gun or not? So that's the base rate of people in New York who are carrying an illegal gun. Okay, 20% of those people are people of color and the rest are white. 25% of those who don't carry guns are people of color and the rest white. I'm sorry, I'm actually not going to, I don't actually remember how much trouble I put into figuring out if these numbers are right. I think I just came up with them to try to get things to go qualitatively in the direction of the truth. So the question is, what is the correct probability, the Bayes rule probability, that a person of color is carrying a gun? So I'm going to leave you to do this. You can do it alone or in groups. Just do the math. I want you to convince yourself you can do this. Carrying a gun, what I mean is carrying a gun illegally. I think it's extremely hard to carry a gun legally in New York City. So raise your hand if you'll get it in 1 more minute. Okay, take 1 more minute. Okay, why don't you guys go ahead and click in. 5, 4, 3, 2, 1. Everybody in? All right. Everybody else is in Cabo? Fine. All right. So modal answer is A. Is anybody confident enough of whatever answer they submitted to be willing to walk us through the solution? Yes, Priyanka. Sorry, I'm going to ask you to speak a little bit louder. Okay, so you did a tree. We have gun, that's 0.05. No gun, 0.95. You want a tree, we have POC, we have white. POC, white, yeah? 0.2, 0.8. Okay. So probability that you are carrying, that you're a person, sorry. So the probability that you are carrying a gun, if I see that you're a person of color, is, so that's the probability that a randomly selected person is going to be both a person of color and carrying an illegal gun. So 0.05 times 0.2 is equal to what? 0.01. Fine. And then you skipped this, I bet. And you went to here. Okay, what do we get? 0.2375. And so you take that and you divide it by that plus that. Is that right? Okay. What is this in terms of probabilities? Somebody here was starting to say it. So this is the probability of B of O. That's the probability of POC. Yeah, okay, so in terms of, so this is the probability of the hypothesis and the signal being true at the same time. But let's break that down. It's the probability of a person having a gun multiplied by the conditional probability that they would be a person of color carrying a gun, okay? This is the probability the person is not carrying a gun times the probability that a person not carrying a gun would be a person of color, right? So we're very close to Bayes' rule, right? Bayes' rule was sort of, right, this is area A in the diagram. This is area B, so it's the ratio of this thing to this thing plus that thing, okay? My hard drive space is low. That's unfortunate. So it's the probability that you're carrying a gun and that conditional on carrying a gun, you are also, this is like Pee-wee's Great Adventure. Conditional on having a gun, divided by that same thing, sort of area A, all right, times probability of being a person of color conditional on carrying a gun, plus the probability of being someone who is not carrying an illegal gun, times the probability of such a person being a person of color. And the answer, Priyanka, is, it's A. It's 0.04. Okay, that's the math of getting it right. That is to say, that's the rational answer, given these numbers. All right. Now, let's now introduce our first sort of non-Bayesian, or what we're going to call quasi-Bayesian behavioral alternative to rational probability inference, which is a little thing that we're going to call base rate neglect. So let's recall the HIV test anomaly, right? We had an HIV positive base rate of 1%, and then we had this test that was 99% accurate for positive and also 99% accurate for negative. And if you do Bayes' rule based on those numbers, you get that the probability that someone is in fact HIV positive if you see a positive test, that is to say the probability that a positive test is a true positive, is 0.5. Not so great. The modal answer of UC Econ students and lots and lots of other people is 0.99, which, as Andrew pointed out last time, looks a lot like they're just ignoring the fact that that a negative person might show up with a positive test. It's just ignoring the possibility of false positives. What we think is, and then the second thing that Andrew said last time was, well, it's not so much that I ignored it. It's just that I know it was there, but I didn't. The math was just a little bit too hard given the stakes. I mean, if I'd offer you $1,000 to get this right, you would have taken the time to do it. Although, if you look at the poor cop from Ferguson right now, you would think that the stakes of getting this stuff wrong is actually pretty high. I'm going to back off from that statement because we can't say with conviction that he was wrong. Okay, so what is the point of all this? We have some notion that in fact what's going on is not so much that people are ignoring the possibility that that a positive test could have come from a negative person, but that they're ignoring how extremely likely it is that a person is HIV negative and how rare it is that someone is HIV positive. And that's called base rate neglect. So Kahneman and Tversky explain that kind of error in terms of what they call heuristics. So there's this paper that I've assigned called Heuristics and Biases. It's arguably the first paper in all of behavioral economics. And they say this: people rely on a limited number of heuristic principles. So a heuristic is a rule of thumb. When you hear the word heuristic, you should think rule of thumb. That's to say a simple shortcut way of getting an answer that's good enough. People rely on a limited number of heuristic principles which reduce the complex tasks of assessing probabilities and predicting values to simpler judgmental operations. Okay? In general, these heuristics are quite useful, but sometimes they lead to severe and systematic errors. And I talked last time about why what we care about is systematic errors, errors that are typically biased in one direction rather than the other. Now, it's important to note that Kahneman and Tversky aren't saying that these heuristics, these rules of thumb that we use, are often quite accurate. They're saying that they're often quite useful, which is to say that in lots of situations, applying simple heuristics will, on balance, get you reasonably good outcomes, even if those heuristics aren't in fact accurate. But then we're going to find situations where they are quite unuseful, quite harmful. So Orbar Hillel sort of was a little bit more detailed in thinking this through. He said people order information by its perceived degree of relevance, and they let high relevance information dominate low relevance information. The base rate fallacy is thus the result of pitting what seem to be merely coincidental, therefore low relevance base rates, against more specific or causal information. So the base rate of how many people in general carry an illegal gun, or how many days in general are rainy, or how many people in general have HIV, seems like this sort of background information that's less salient. You've just learned some new information. Whoa, this guy got a positive test. Or, geez, it sure is cold out. Or, this person's coming at me and they have dark skin rather than light skin. This is new information, and so what Bar Hillel is saying is, his cognitive model is, people place greater emphasis on the information that is in some way more salient, okay? Perhaps because it's new, perhaps because it seems to have more causal relevance. This is just kind of for fun. I like this. This is a paper by Hazelton et al. Effects of error management are cases in which errors that were less costly over evolutionary history are favored over more expensive ones, producing biases in the direction of a less costly error. What on earth is he talking about? So imagine a sort of deeply rooted evolutionary situation where you have this is a classic ancient judgment decision that you have to make. You see something squiggly on the ground and you have to decide whether or not you think it's a snake. So a false positive looks like this. That's a snake, and then you look down and you say, oh no, silly me, it's just a stick, right? And the cost of that is that you feel like an idiot. I don't know if you've had this experience. You're walking in the woods and you sort of leap sideways, and even if there's not someone there, you sort of think, "Oh my God, the fantasy audience that I always carry with me, that's looking at me and telling me what a good person I am, just thought I was an idiot." Yes, you're not alone in having that fantasy audience. That's a false positive. The other possibility is a false negative. You look down and you say, "No, that's just a stick," and it turns out to be a snake, and the cost of that is significantly higher than mere embarrassment. Okay, so what Hazelton et al. Are sort of saying is that evolutionarily, it makes sense that we would gradually tend to favor sort of heuristics, decision-making heuristics, that cause us to make the low-cost error, which in this case is a false positive. Okay, but in some cases, the low-cost choice might be a false negative. One of the great things about evolutionary psychology is that it's not possible to conduct a randomized controlled trial on evolution, so you can say whatever you want. But this is not unreasonable. Okay, and then you have some heuristic that gets baked into and hardwired into your hindbrain, and then it can become costly in a modern setting. So HIV, diagnosing someone with HIV incorrectly could ruin their life. Randomly stopping and frisking people of color can undermine social harmony. I would go further, and I would say it doesn't. It has undermined social harmony. It is actually in the middle of undermining social harmony right now. Okay. Okay, fortunately for us, our job is not to wonder why these things came to be, but just to model it, okay? So, psychological insight is fairly straightforward. It appears that we pay too much attention to the new information, the signal, and forget to account for past experience, which is the base rate, okay? How could we model that? Because I, and by extension you, we're all students of Matt Rabin, we're going to take the Matt Rabin approach, which is to start as much as possible, to salvage as much as possible of the rational model, and see if we can make headway just introducing some behavioral tweak to the rational model. Now, this is a super simplified model that, and I'm not quite sure why, is not actually published anywhere. It's just something I happen to know because I am a student of Matt Rabin. You won't find it written down anywhere except here. But here's how it works. So we're going to call this approach quasi-Bayesian because, as I say, we're going to start out with the framework of Bayes' rule. We're going to assume one simple thing. We're going to use Bayes' rule, but we're going to assume that people put the same probability on all possible hypotheses. In other words, they treat all base rates as equal. Now, in Bayes' rule, so if you think about the rainy versus not rainy, the base rates are here. The probability, the unconditional probability that any randomly selected day will be rainy or not rainy. The way this model works is you write down Bayes' rule, and then you just treat all of these base rates as being equal, which is another way of saying you completely ignore them. Because if the base rates are all equal, they cancel out. Okay? So that turns Bayes' rule into this. And now all we're looking at is the conditional probability of seeing a signal given some underlying hypothesis that we don't observe. Okay? We're now basically doing something that looks Bayes-like using only half the information. Okay? Using only the new information. I'm starting to struggle with board management. So in the case of the HIV test, right, we get, now of course I've stacked the deck in this example so that I get exactly what I want. Right, so the probability of someone having HIV conditional on having a positive test result under Bayes' rule, right, it's the probability that they're positive times the probability that they test positive if they are positive, divided by, all right, I'll write it out again. This is where you get tired and you'll want to skip steps. That, right, plus the other way that you could see a positive test, which is that they are HIV negative and yet nonetheless test positive, right? And now all you do in the model is to set the probability, the base rate of being HIV positive equal to the base rate of being HIV negative. That goes away, that goes away, and that goes away. And if you plug in the numbers, right, the probability of getting a positive test if you're positive is 0.99. This is our modeling assumption. Okay, it's 0.99 over 0.99 plus the probability that an HIV negative person would come up with a positive test result, which is 0.01, and that's just 0.99 divided by 1, which is 0.99. Lo and behold, that's the modal answer. Boom, looks like people are doing base rate neglect. Sorry, looks like a model of base rate neglect can explain the answer. Doesn't prove that that's the right model, but this model gets much closer to what we observe than the standard model. Okay, so this is, again, kind of a horse race. Okay, this model does a better job. There might be some other model that would do an even better job, but this one does a dramatically better job than, we should just pay someone to take photos of all the boards, right? No, you should. This is perfect. And then you can put it on DSpace if you want. Well, you can send it to me and I'll put it on DSpace. Or I could just give everyone opera glasses. So that's how you implement this model. It's a very dumb model. Okay, you could easily imagine coming up with a much more sophisticated model of base rate neglect. And to be honest, it's a puzzle to me why that doesn't exist in the literature. And if you can find a more sophisticated model of base rate neglect, please let me know. But this does a lot of work for us. Now, I should warn you that the reason this comes up with exactly the modal answer is by convenience, because I made the sort of failure rate for negatives exactly 1 minus the success rate for positives. Okay, that's not always going to be true. What's always going to be true is that the inferred probability is always going to be inflated if the base rate of the hypothesis that you're inferring is less than 0.5, right? So this is the case where we're trying to come up with the conditional probability of a hypothesis that is very rare, much less than 0.5 probability that you're HIV positive. Base rate neglect is always going to inflate that, okay? And base rate neglect would deflate the probability that you're negative given a positive test, okay? So that's something that you'll see in more detail in the problem set. Okay. So you now know all the math you need to know for the problem set. All right, now we're going to do that math in the same setting as before. Okay, so this is a base rate neglect. This is a police officer subject to base rate neglect. Okay, so what we want to see is if this simple model of base rate neglect can, in some sense, explain the choices of a the average New York City police officer or the police department as a whole, if in fact this is a policy that's established at the department level. Same numbers. These probabilities are the same. So I just want you to apply this simple model of base rate neglect and tell me what prediction it makes as to the inference that somebody would make.